I've explained in the first lecture that there are two parts, two sides to a smart contract, an on-chain part and an off-chain part. The on-chain part is about validation. It allows nodes to validate a given transaction and decide whether the transaction is valid and whether it's allowed to consume a given UTXO. And the off-chain part lives in the user's wallet and constructs and submits suitable transactions. So both are important topics, and we have to master both in order to write smart contracts. But for now, I want to concentrate on the on-chain part. So let's recall the extended UTXO model, where the idea was that we introduce a new type of addresses. So the type of addresses used in the simple UTXO model is so-called public key addresses, where the address is given by a public key or the hash of a public key. And if a UTXO sits at such a public key address, then a transaction can consume that UTXO as an input if the signature belonging to that public key is included in the transaction. And what the eUTXO model does is extend this by adding a new type of addresses, so-called script addresses, that can run arbitrary logic. And then when a transaction that wants to consume a UTXO sitting at a script address is validated by a node, the node will run the script and then, depending on the result of the script, decide whether the transaction is valid or not. And recall that there were two more additions. So one was that now instead of just having signatures and transactions, we have so-called redeemers, arbitrary pieces of data. And on the UTXO side, on the output side, we have an additional arbitrary piece of data called datum, which you can think of as a little piece of state that sits at the UTXO. Finally, we have the context. And then I explained last time that there are various choices what this context could be. It could be very restricted, just consisting of the redeemer, or it could be very global, consisting of the whole state of the blockchain. But as I said, in Cardano, it is the transaction that is being validated, including all its inputs and outputs. So there are three pieces of data that a Pluto script gets: the datum sitting at the UTXO, the redeemer coming from the input under validation, and the context consisting of the transaction being validated and its inputs and outputs. So in a concrete implementation like Plutus, these three pieces of data obviously have to be represented by some concrete data type, a Haskell data type. And as it happens, the choice was made to use the same data type for all three of them, at least at the low-level implementation of Plutus. So we'll look at that first, but in real life, nobody would actually use this low level, and there are more convenient ways to use more suitable data types for these things. And we'll come to that a bit later today. But first I want to talk about this low-level implementation of validation. So datum, redeemer, and context all use the same Haskell data type, and we'll look at that first. This Haskell data type is defined in the package Plutus-core in Plutus-core source Plutus-core data. And it is called simply data. And if we look at the definition of this data type, we see it has 5 constructors and is a run-of-the-mill algebraic data type. So it has 5 constructors: constr, takes an integer and recursively a list of data. Then a constructor map that takes a list of pairs of 2 data items. So you can think of it as a lookup table with key value pairs where both the key and the value are data again. Then the list constructor that takes a list of data, the I constructor that takes an integer, and the B constructor that takes a string, or rather a byte string. And for those of you who are familiar with the JSON format, for example, this is very similar to something like JSON. I mean, the constructors are not exactly the same, but like JSON, it can represent numbers and strings and lists of data and key value pairs. So it's what I would call, even though that's probably not an official thing, I would call a blob type. So it can basically represent arbitrary data, which makes it very suitable for our purpose, because when I explained the extended UTXO model, I was always talking about arbitrary custom data. We can play with this type in the REPL. So I'm in this week's code folder and I fire up a REPL with Cabal REPL. Now, in order to get access to the data type, I can import PlutusTX. It wasn't defined in PlutusTX, but it gets exported or re-exported from PlutusTX. So if I do :I for info and ask for information about the data type, then I basically see the same that we just saw in the source code. And here we also see where it is actually defined. Now I can play with this, so I can try to define values of this type. So for example, I can use the I constructor with an integer, so I42. I can ask for the type, and that is indeed of type data. If I want to use the B constructor, I need a byte string, and the easiest way to quickly get a byte string is to activate an extension, a GHC extension that's called overloaded strings. And what that overloaded strings extension does, normally in Haskell, literal strings are of type string, the Haskell string type, which is just a synonym for lists of characters. But with this extension, I can use literal strings for other string-like types as well. And one of those string-like types is the byte string type. So now that I have this extension, I can use the B constructor, for example, Haskell, and I get, again, something of type data. And of course, I can also use the more complex constructors like map. So if I have map, and now I need a list of pairs of data, key value pairs. So for example, one key could be I42 and the value could be B Haskell. And the key can also be more complex. So I can, for example, use the list constructor, I don't know, I0, and as value I1000. And again, I get something of type data. In order to write our first validator, I create a new Haskell module. I call it gift. And I more or less just copy-pasted all the language extensions and the imports from last week's auction example. Now let's write the validator. And of course, the validator itself in the end will be a script living on the blockchain in Plutus Core, a low-level language based on the Lambda calculus. But we don't have to write Plutus Core, we write Haskell. And I will explain later how we convert that Haskell into Plutus Core script. So we write a Haskell function that represents our validator. Let's call it makeValidator. So what is the signature of this function? As we know from the EUTXO model, these validation scripts, these validators, get three pieces of information: the datum, the redeemer, and the context. The datum comes from the output that is being consumed. The redeemer comes from the input that is consuming. And the context is the consuming transaction with all its inputs and outputs. And as I just said, at this low level, all three types, datum, redeemer, and context, are represented by the data type that we just looked at. So this will be a function that takes three arguments: all of type data. And it so happens that the first one is the datum, the second one is the redeemer, and the third one is the context. So now what is the return type? And that is somewhat surprising. It's unit. So this opening, closing parentheses is the unit type in Haskell. It's a built-in type, and it is similar to the void type in mainstream languages like C# or C or Python or Java. And this type, the unit type, only has one value, which is also called unit. So if we go back to the REPL, if we start up a new REPL, and let's load this module called gift. So there's this value, it's also called unit, and it looks exactly like the type unit. And if I ask for the type, then it's of type unit. And that is the only value. So that means this type or value of this type doesn't carry any information because there's only exactly one value of this type. Now, if you are somewhat more familiar with Haskell, you will be surprised about this signature, because in Haskell it's very rare that we have a function with a return type of unit. In mainstream programming languages, you often see functions or procedures with a result type of void. And the value of such functions lies in the side effects. The end result is not interesting. A void result, or in the Haskell case, a unit result, carries no information, as I just said. We know what the result of the function will be. It will be unit. So why would you bother writing such a function? Now, in other languages, the reason is that in other languages, functions can have arbitrary side effects. So a function with return type unit in Java, for example, could write something to the screen, or do networking, or access the hard drive, or whatever. In Haskell, that's not possible, not with this signature. That would be indicated by an IO to indicate that it has side effects. I'll get to that a bit in a later lecture. So this is very unusual, and the way it works is there is one thing that a Haskell function can do apart from returning a result, and that is it can have an error or an exception. It can fail. So the way validators work at this low level is that if there's no error, then validation passes, and if there's an error, then it fails. So in order to write the simple-most validator possible, we can write a validator that completely ignores all three inputs and always passes. So we can ignore by using underscores for the inputs. That indicates that we don't care about their value, and we simply return unit. So this is arguably the simplest validator you can possibly write. It completely ignores its three arguments. It doesn't care about the datum, it doesn't care about the redeemer, it doesn't care about the context, and it immediately returns unit without having or producing an error. So that means it always passes. It doesn't care what datum, redeemer, context are, it always passes validation. And what does that mean for the corresponding script address? So recall, a script address is more or less the hash of the validator. So I'll show in a second how we turn this Haskell function into Pluto's core script. And then if you take the hash of that script, you get the address, the script address. So what would it mean to have an output sitting at the script address? Well, it would mean that arbitrary transactions can use that output as input. Arbitrary because it doesn't matter what redeemer is used, it doesn't matter what datum was used at the output, and it doesn't matter what structure the transaction that consumes that input has. So that's why I called this module gift, because if anybody sends funds to this script address, then anybody else can immediately consume that output and use it for their own purposes. So if you send Ada to this address, it's a gift. Anybody can immediately take it. we should check in the REPL, we should reload, and let's ignore the warnings. That's just unused imports, so we don't get an error. We should always frequently switch between the REPL and the editor and save our work frequently and try to load it into the REPL to see that everything is still fine. It's a nightmare if you write hundreds of lines of code without ever checking whether it compiles, and then you get hundreds or thousands of compiler errors. So ideally your program should always compile. So I made it a habit to very frequently save my work and check in the REPL whether it still compiles. Now that we have defined this Haskell function, we want an actual validator. And that is of type validator. And in order to get the validator, we have to compile this function to Pluto script and take the script to create a validator. So let me first write down how we can do this. And it uses an advanced Haskell feature called template Haskell. And I'll explain it in a minute. But the good news is that the pattern how this is used in order to work with Plutus is always the same. So you don't really have to understand the intricacies of template Haskell in order to use it. It's more or less always a copy-paste of the same pattern. Okay. Let's first look at the types in the REPL. So I start the REPL again with Cabal REPL and load the module with :L module name. And now I need to import Ledger scripts and Plutus TX. Now let's first look at the type of make validator script. Okay, so it produces a validator, which is what we want, but it takes something that's of type compiled code parameterized by data to data to data to unit. So this already looks promising because this is the signature of our make validator function. So that, I mean, as the name suggests, this type indicates is the result of compiling a Haskell function of this type. So let's check what the type of compile is. Okay, and that looks a bit scary, but it's mostly because of these qualifications here. So what this says is it takes an expression of type A and compiles it into something of type compiled code of type A. So in our case, we apply this where A is data to data to data to unit. So we must somehow plug in something of this type, the syntax of something of this type, and we get out the syntax of something of type compiled code A. So now what's this syntax business? This is where template Haskell comes in. So template Haskell does what other programming languages solve with macro systems. So macro, what's a macro? A macro is something that gets expanded before the compiler runs. So it's basically at compile time, macros get somehow evaluated and expanded into code that's then inserted next to the code that the user manually typed, and then the compiler is run over all of that. So the user code and the expanded macros. So it's a way to basically generate code at compile time. So macros are, another expression for macros is programs that write programs. And in Haskell, this is done with template Haskell. So template Haskell allows you to write Haskell functions that produce other Haskell functions or Haskell types or general Haskell expressions, and insert those into the source code and then run the compiler over that to compile the program and then actually run it. Right, and So these expressions, this syntax stuff, this is the type of Haskell code. So something of type expression A, if you have Haskell, for example, of type int, if you have an int, then exp int would be a piece of code that represents an int. Okay, so we need a piece of code that represents something of type data to data to data to unit. I mean, we have our makeValidator function, but that is a Haskell function. It's not code. So somehow having this function, we must get our hands on the code of that function, the actual syntax, the syntax tree. And this is what these so-called Oxford brackets are for. So they allow us to quote, the technical term is quote. So having some Haskell expression, we can quote it using these brackets to get at the underlying syntax tree. Okay, so this is the first part. So we have our makeValidator Haskell function. We put it in these Oxford brackets. So the result of that is the syntax tree defining this function. So in principle, you can imagine that the result of this is something like this string that defines the actual function. It's not really a string, it's a more complicated data type, but you can sort of think of it like that, that this is now this piece of source code. Okay, and that is exactly what the compile function expects. And it compiles it and produces another syntax tree, but now Pluto's core syntax. So out comes basically the syntactical representation of the compiled makeValidator function, now in the programming language Pluto's core. But this makeValidator script doesn't expect syntax, it expects an actual script. And this is now what the double dollar is for. That is in a way the opposite of the Oxford brackets. So the Oxford brackets take an expression, a Haskell expression, and convert it into a syntax tree of that expression. And the $$ is a so-called splice, and it takes a syntax tree and splices it into the source code at that point. So this here gives us basically the Pluto's core syntax tree. And by using this $, in the first pass of compilation, before the actual compiler runs, this will run. So we get the Pluto's core syntax. And then you can imagine that at this point where the $$ is, this syntax will be spliced in. So that is as if we had hard-coded instead of this, if we had hard-coded the correct Pluto's core expression at this point in the source code. And then the makeValidator script function takes this and turns it into a validator. But as I said, you don't really have to understand it because it's always the same pattern. We will see a somewhat more complicated pattern for so-called parameterized script in a later lecture. But once you have seen a couple of examples, it always follows the same pattern. But still, it might be good to understand what's going on. So we have this Haskell function that has the logic. You use the Oxford brackets to convert that into a syntactical representation of this function. Then compile takes that syntactical representation of that Haskell function, turns it into a syntactical representation of a corresponding Pluto's core function. And then the $$ takes that Pluto's core and splices this into the source code at this point. And then it is as if we had manually typed makeValidator script and then a complicated expression for Pluto's core. And that then turns that into a validator. Unfortunately, there's one additional thing you have to do. Normally, these Oxford brackets don't allow you to reference definitions outside of them. So normally, you have to inline all your code into these brackets. So in our case, with this extremely simple validator, that wouldn't be a problem. We could easily not have defined this makeValidator function and just inline here in the brackets wrote this expression. But of course, you can imagine that realistic Pluto's validators will be much more complicated, and you will also want to use helper functions or maybe even library functions that are defined elsewhere in order to avoid code duplication. And you want to maybe reuse pieces of code also in the off-chain part of your contract. So you don't want to inline everything into these brackets. You want to have separate definitions of the validator and helper functions. And normally that wouldn't be allowed. But we can fix this by adding a so-called pragma to our makeValidator function. And that's the inlineable pragma. And as argument, it takes the name of the function we want to make inlineable. So makeValidator in our case. And this curly brackets minus hash minus curly brackets. This is just the syntax how you do pragmas in Haskell. So by adding this, we allow the compiler to inline the definition of makeValidator inside these brackets, these Oxford brackets, and then it's fine. And we would do the same for helper functions that are maybe referenced in the makeValidator function. So if you look at the source code of Plutus, then in certain libraries, especially in the Plutus Prelude, you will see this inlineable pragma all over the place. Virtually every function there has that. And that is always a good indication that those functions are meant to be used in validators in on-chain code. Because everything that's supposed to be used in on-chain code needs this pragma. If you go back to the REPL and type validator, then it seems to work, but I mean, we don't see much because where the Plutus core script is, it's just indicated with this word script. But we can ask for the definition of validator, and we see it's just a new type wrapper around a script, so that we can get access to with get validator. So let's try this. If we have get validator, okay, that's also not very enlightening. We just see script. But if we ask for information on script, we see we can unwrap that with unscript to get something of type program. So let's try this. And we see something. I mean, it looks very complicated, and those of you who have seen lambda calculus before will spot that this is some version of the lambda calculus that uses De Bruijn indices for variables. But I mean, here you can see the actual honest to God Plutus core script in this representation. So it worked. We did compile something. We did compile our makeValidator function and turned it into Plutus core. So now we have our first validator. Given this validator, we can create values of two related types that will also be important. One is validator hash. So as the name suggests, it's basically just the hash of the validator. And we can turn our validator into a validator hash by using this validator hash function. So I call the result valhash. And also, given the validator, we can turn it into an address. So this is a real address on the blockchain. So we no longer only have pub key addresses, we also have script addresses. And this is how you get it. So you apply the function script address to the validator and you get an address. So let me reload and see whether we see anything. Okay, so the validator hash indeed looks like a hash. Yeah. Script address. Okay, and we see this is more or less just given by this hash. So the so-called script credential is just this validator hash. And then there are other informations in an address. We see there's something staking related. So an address can also always contain staking information so that it stakes to a given stake pool. But we see essentially the script address just consists of the hash of the validator. And it is important to keep in mind that most of this code is boilerplate. So the actual business logic, the validation logic in this example is just in this line where we say validation always succeeds, no matter what datum or redeemer or the transaction that spends it are or look like. Then the rest you will see in this form are very similar in all Pluto's code. So the way to take this Haskell function that gives the business logic of validation and turns it into an actual validator by compiling it to Pluto's core script, and then how to take that validator and turn it into validator hash or an address. So this is just boilerplate. The only interesting line is line 34. Now, of course, in order to try this, we also need an off-chain part. And because the focus of this lecture is on validation on on-chain Plutos and not on off-chain Plutos, I've already prepared this. So this is that. And I don't want to go into any detail, but just briefly go over it. So this type definition defines the so-called endpoints. Endpoints are ways for the user to trigger something and enter data, give input parameters. So in this case, I want two endpoints, give and grab. Give takes an integer parameter, grab doesn't take any parameters, which is represented here by giving a unit parameter. So the idea is that somebody can send money, ADA, to the script address we just defined, and the integer argument specifies how many loveless. And the grab endpoint is for people that want to spend such addresses, so that will just look for all UTXOs sitting at this gift address and creating a transaction that grabs all of those and sends them to the user wallet. Then next I define the actual behavior of these two, give and grab. So give taking the integer amount of loveless I want to put at that address. So I create the transaction by specifying constraints. So this says must pay to other script. So this transaction should have an output at a script address, which is given by the validator hash. So this is our script address that we just defined. And this is one of the points where you need this validator hash with a given datum. So because of how we defined our validator, the datum is completely irrelevant, but I must specify one. So I just pick an arbitrary one. And then I must specify how much funds. So ada.loveless value of takes an integer and converts it into loveless. So this says the transaction must pay this many loveless to that script with this datum. Then this line submits that transaction. This line waits for confirmation of the transaction. And that line logs information. So in the playground, for example, we can see these log messages. So that just logs the line made a gift of so and so many loveless. Now the grab endpoint, no parameters. This line looks up all UTXOs sitting at this address. So this is our script address. So this will find all UTXOs that sit at that script address. Then this line gets all their references to these UTXOs. Then I need to so-called lookups in order to tell the wallet basically how to construct the transaction. So I tell it where to find all those UTXOs, and I also inform it about the actual validator. Remember, I explained earlier, if you want to consume an UTXO sitting at a script address, then the spending transaction needs to provide the actual validator code, whereas the producing transaction only has to provide the hash. So this grab is now a spending transaction because I want to grab all the UTXOs. So I must somehow include the actual validator in that transaction. This is what that line does. And then I define the transaction, again, giving constraints. So in this case, I have a list of constraints, one for each UTXO that I found here. So for each UTXO sitting at this gift address, I say, okay, the transaction I'm constructing must spend that UTXO. And I must give a reference to it. I must provide a redeemer. And again, the redeemer gets ignored by our validator, so I can do something completely arbitrary. So I pick this one here. And that's it. So this line basically says, okay, construct a transaction that spends all those scripts outputs sitting at this address. Then there's a variation of the submit tx I used in line 78, submit tx constraints with, that also takes these lookups. So that allows the compiler or the wallet to construct a transaction that has the necessary information, how to find those UTXOs and the actual validator script. Then again, I wait for confirmation and I log a message, collected gifts. And finally, I put it all together in this endpoints function. And that basically says, okay, the select is it offers the user choices. So this means make available give prime or grab prime. And then afterwards recurse and do the same over and over again. And give prime in principle just uses our give that we defined above, but recall the give needs an integer argument. And this endpoint give, operationally what it does is it will block execution and wait for the user to provide an integer. And once that is provided, execution will continue and will pass on this integer argument to this give function. And similar for grab, except that grab doesn't expect any argument, so this will just block until the user unblocks it and then run the grab function. And because of this select, that means at every point in time we have these two options. We can either provide an integer and trigger the give, or we can not provide anything and trigger the grab. And after the give or the grab has finished, we are again presented with the same choices. So this wraps up all the functionality we want for this example in this one function. And then there is some boilerplate to generate schema for that. And this make known currencies so that in the playground we have Ada available. Let's test this in the playground. So I started a local playground as I explained in the first lecture and copy pasted the code into the editor, and I compile. And simulate. Okay, let's use 3 wallets and give each, I don't know, 10 ADA to begin with. So 10 million Loveless. And let's say that first both wallet 1 and wallet 2 invoke the give endpoint. So see this give and grab, that's exactly the two endpoints I defined in my off-chain code in the endpoints function. And the playground picks that up and renders a UI for those. So I must specify how much. So let's say wallet 1 gives 4 ADA, 4 million Loveless, and wallet 2 3 ADA, 6 ADA. Okay, then let's wait 1 block to give those a chance to be incorporated into the simulated blockchain. And now wallet 3 grabs. So grab doesn't take any parameters. And let's wait again for 1 block to allow the grab transaction to get onto the blockchain. Now evaluate. Okay, and we see 4 transactions. So the first one is, as I explained last time, always there. That's the Genesis transaction that distributes the initial funds. We can see that here. So that gives 10 ADA to the wallets 1, 2, 3. Now these two are the give transactions, and they both happen in the same slot, in slot 1, because I didn't put a wait in between those. And the grab happens in slot 2. So let's look at the first one. This happens to be the give of wallet 2. So the other one is the give of wallet 1. So we see the order here doesn't reflect the order in which we did it in the simulator. which makes sense because in the real blockchain that's also indeterministic. It depends on the timing between those two wallets. Okay, so wallet 2, so the input is the one UTXO that wallet 2 had, that comes from the Genesis transaction, the 10 ADA. And then there are some fees, 10 Loveless in this case. Then this is what goes to the script. No, sorry, this is the change. So 4 ADA minus fee go back to the wallet. And this is the script. So this is our shiny new script address that we got. Remember, we defined the validator and then hashed it, and the hash of that, the hash of the validator is more or less the script address. And we see that now 6 ADA sits at that script address. If you look at the other GIF, it's very similar, except now it's wallet 1 instead of wallet 2, and the amounts are different because here we only gave 4 ADA to the script. So 6 ADA minus fee are changed. And finally, grab. So the off-chain code scanned the blockchain for UTXOs sitting at the script address and found those two and uses both of them as input, and then has to pay some fees. In this case, significantly higher than just 10 Loveless. This is because now scripts are actually executed. So script execution makes it more expensive, the transaction. But I don't know whether those costs are realistic yet. Probably they are not. But we do see that having scripts that need to be validated has an effect on fees. The amount will probably still change until it's fully calibrated. And the sum, so the 4 and the 6, 10 minus fees go to wallet 3. So wallet 3 successfully grabbed those two UTXOs, used them as input for this transaction, and the output is to wallet 3's own address. If we scroll down, you see how many balances are there in the end. So we see wallet 1 ends up with 6, more or less, wallet 2 with 4, and wallet 3 with 20. The initial 10 plus the 6 and the 4 that it grabbed from the donations made by the other players. We also have logs and trace. I can see some more detail about the execution. So yes, that's the arguably simplest validator you can write. And it's of course a bit stupid and silly, but it might even in some situations be useful. If somebody wants to, for whatever reason, give ADA away to the community, then in principle this script address could be used. For our next example, I just copied the gift module that we looked at just now and to a new module, and I call that one burn. But right now the code is identical, so everything is exactly the same. So the first example, the gift example, was a validator that always succeeds. It ignores its 3 arguments and always succeeds by returning unit unconditionally. So in this example, in the burn example, I want to do the opposite. A validator that again ignores all its 3 arguments, but then always fails. So how do we do failure in Plutus, in a Plutus validator? We have error function for it. Let me go to the REPL and load the burn module. If I ask for the type of error, I see that it takes a string and returns an arbitrary type. But this is not the error I am using in the code. This is the standard Haskell error coming from the Haskell prelude. So in order to look at the error I'm using, I must import Plutus TX, or I must qualify it with Plutus TX.prelude error. So this is the one I'm using. It takes a unit and returns an arbitrary type. And this brings us to an important point. I mentioned before, when I explained this inlineable pragma, that whenever you want to use a library function or a helper function inside the validator, in order for the template Haskell mechanism to work, everything must be inlineable. So this inlineable pragma has to be added. But in the standard Haskell prelude, of course, that's not the case because the standard Haskell prelude is like decades old, and nobody had Plutus in mind when that was written. So for that reason, the Plutus team has provided their own version of a prelude that's suitable for Plutus. And this is here in PlutusTX.prelude. And a lot of functions types defined in the standard Haskell prelude have an analog in the PlutusTX prelude. The problem is that normally in Haskell by default the standard prelude always gets imported. You don't have to import it explicitly, it always gets imported automatically. And if that was the case here, then we would have a lot of name clashes between names in the standard prelude and names in the Plutus prelude. But there is a GHT extension for that, this no implicit prelude. So by adding that, the standard Haskell prelude does not get automatically imported. And by adding this line, we import the Plutus prelude instead. So that's why here when we just say error, we don't get the standard Haskell error that takes a string, but instead the Plutus error that takes a unit. If you look down here, I do import something from the standard Haskell prelude as well, but that's for other reasons that have nothing to do with validation. That is for something in the off-chain code and for the playground to work. For example, the I/O I need to import so that the playground doesn't complain. Another thing is that it can be confusing. I mean, a lot of the definitions that are in the standard Haskell prelude and in the Plutus prelude do have the same signature and the same behavior, but that's not always the case, and error is an example. So the standard one takes a string and the Plutus one does not. So one has to be careful. Sometimes code that should work, I mean, if you have some experience with Haskell and use some ordinary things from the prelude, then in Plutus they suddenly might not work anymore or might work differently. I also noticed that there are issues with preferences, sometimes operator precedences. So arithmetic expression or some other combination of operators that would work fine without parentheses in the standard Haskell prelude suddenly doesn't work in Plutus, and you have to add some parentheses. So you have to be a bit careful there. Okay, but with this one change, we should now have a validator that always fails. And if I leave everything as is, I can try this in the playground. I replaced the code in the editor with this change code where only the one line has changed, replacing unit with error unit. And my scenario, my simulation is still there. I think the playground keeps that if the endpoints haven't changed, and we still have the same endpoints with the same signatures. So let's evaluate. Now we see we only have 3 transactions, so the grab obviously failed, which is expected. The GIF should still work. As before, we can send our funds to that new script address, but it should be impossible to retrieve the funds from there. And if we scroll down, we see Wallet 1 and Wallet 2 have made their gifts, but Wallet 3 was not able to grab them. And if we look at the log, we see an error here, wallet error, validation error, script failure. So we see validation failed. The first example, as I said, was of a validator of a script address that allows arbitrary transactions to consume outputs sitting at that address. And now we have the opposite, where something sitting at that address can never be retrieved. So it's locked at that UTXO forever. No following transaction can ever use those outputs as inputs. And that's why I call it the module burn, because it's a way to burn your funds, make them inaccessible forever. So that also in some circumstances might turn out to be useful. One thing that's somewhat unsatisfactory is that we don't see why validation failed. We just get this evaluation error. So there's a way around this, a variation on the error function. So if we check the type of PlutusTX prelude trace error, That takes a Pluto string and produces an error and results in an arbitrary type. So one thing we can do to somewhat improve this is to use trace error instead. And then it doesn't take unit, it takes a string, so we can use a literal there. So for example, let's just say burned. In order for this to work, we have to use this overloaded strings extension that I explained earlier when we wanted to produce a byte string. As I said, normally string literal only produces a Haskell string. So if we wanted to also produce a Pluto string, we also need this. So let's try again. Okay, now it compiles. I replaced the code in the editor and evaluate it again. We again only get 3 transactions. But now if we scroll down, we see here in the error message that this log string, the string we defined in the code, is now visible here in the playground trace. So we get some information what went wrong, at least in the playground. As our next example, let's write a validator that does not completely ignore all its arguments. So let's say we want a validator that expects a specific redeemer. So we do care about the redeemer, and recall the first argument is the datum, the second is the redeemer, the third is the context. So the redeemer is this one. So let's call that R. And let's say validation should pass if the redeemer is I42, integer 42. So using this guard, so we can say if it is I42, then we return unit, so it passes. Otherwise, it fails. Okay, let's see whether it compiles. It does not. Oh yeah, I copied the original gift. So I must again have this overloaded strings. Okay, so far so good. Now we should also change the off-chain code in order to try it out, because I would like to try it out with the correct redeemer and also with the wrong redeemer and see that in the one case it passes, in the other it fails. And I think the easiest way to do is to also provide an integer argument to the grep endpoint. So here, let's call that n. And then instead of hard coding the redeemer to I17, I just use in. And then I also have to change this here, because now it also has an argument, so I have to pass that on to grep. Okay, that compiles. Now if I go to the playground and I replace the code in the editor with our newest version and compile it, and now we see that the scenario I prepared for the gift and the burn is gone. And that is because now the endpoints have changed. Now the grep endpoint suddenly takes an integer parameter. So in that case, this is gone and I have to redefine the scenario. I think in this case, it's enough to just use 2 wallets, but let's increase this to 10 ADA each again. Okay, let's say wallet 1 gives maybe 3 ADA. We wait 1 block. Now wallet 2 grabs, and let's first use the wrong redeemer. So for example 100, and wait again. And let's try it out. And we expect grep should fail, because this now uses as I1, and validation will fail in that case. It should only pass if it's I42. Indeed, we only have 2 transactions. So this is the Genesis transaction and the give transaction, but grep failed. If we look, so wallet 1 gave the 3, but wallet 2 didn't get them. And if we look at the trace, we see validation error, wrong redeemer, as expected. Now let's go back and change the 100 to 42 and try it again. And now it seems to have succeeded. We see the third transaction. And indeed, Wallet 2 is able to get 3 ADA minus fees. You also see this here in the diagram. Wallet 2 now has 13. And the error is gone. So that's the first example of a validator that actually looks at least one of its arguments.